Hello everyone and welcome to the new demonstration, that is Demonstration-4 on digital image processing software. In this one we are going to discuss three demonstrations or three techniques which we have already covered in our discussions or in lectures. One is the convolution filtering. I will be showing how you can edit the available filters in a given software, and then principal component analysis, and one more technique is the decorrelation stretch. So, first I will go to this demonstration. In this software, as we have been using this image, so I will continue to use that spot image of Moscow, and then what we go for checking this filtering technique, and in this one we go here for your home, and then multispectral and this filtering option here. So, we will go to filtering options, and here we go for convolution filtering. So, lot of already ready-made filters are there, and whenever I choose any of these on this right side on the image itself, and the effects are taken and the preview is shown basically. So, if I accept any of these, this is what I will be getting results. For example, like this. So, I can choose any one, but I would like to so that one can also do, like suppose if I go for edge enhancement and using a 7x7 filter, this is how this filter looks. So, because there are it's a large filter, and the center value is of course plus 97 because this is high pass filter. So, the local variations would be highlighted, and regional variations are reduced. Therefore, all other cell values of this convolution filter are negative or -1, and so, but if I want to change the size here, I can design my own filter. So, I can change the size like from 7 automatically it will go to 9, and then 11 I can choose 11 by 11. And then I have to provide the values for all these things, and once that is there, then I can execute this convolution filtering. So, lot of options are there already in the software. So, different softwares of course will provide a different kind of filters, and one can also design. If I see the example of low pass filter, and that too of 11 by 11, as you can see here, there are 11 rows and 11 columns are there, and in the since it is low pass filter, so every value is 1. So, lot of averaging will be done, and then you will get results accordingly. But if you want to see a quick review of what you are going to have, on the right window automatically it comes very quickly here. So, that is the there are other well known, well established filters like Sobel 1, 2 and 7 by 7, 5 by 5 and directional filters. All kinds of possible filters which one can think are already inbuilt, but still one requires, as per his requirements, can also edit, design his own filter and then execute things accordingly. Now, we will be on the same image, we will be looking this your principal component analysis. So, when we go for principal component analysis, what we find here that this is the option which is available through spectral buttons, and here we can choose whether I want to perform on the whole image or on a small image, and then I can, of course, I have to provide the place where I will keep. So, I am keeping here, and then I can say that coordinate from where these will come. So these details can also be provided. I will say that show the in the session log, and also write these eigenmetrics and eigenvalues like this. So these can also be written in the location which I will provide. So location I am providing is temp here, and same here I am providing the location temporary folder on the C drive. Okay. And once you go, you can also open the log later and can see the metrics as well. So I say okay. If it is a big file, one can go in batch mode, or one would like to perform on multiple, and there are some other options are also there. So for time being, I am not, of course, how many components are desired, since it's a 3 bands false color composite. So all 3 components are desired from this. Now processing might take some time, and it will keep showing us the status, and once it is done, then you can see individual components as well. As you know that in principal component, the maximum variability will come in the component 1, and in component 3 you might be having the minimum variability, or just noise component might be there. If we would have say 6 band scenario like in Landsat TM, then we can not including bands, thermal band. So I am saying 6, otherwise there are 7 bands. So if I take the 6 band scenario, then the last band I may go for 6 components, and last component will have completely noise there. So likewise I can get those values very easily. Now I will go and check that where it has kept the of course these files would be there, but let me go for this these are the 2 files which it has created, and if I open these files, I will find, maybe in Notepad I can open, and then I will find these both eigenvectors and eigenmetrics also. So one can get the statistical information about the principal components. And secondly, of course, I will get the image here. So let's have image also. So I open that one, go for this, and this is the image which has been created here, and this is these components are here, and I can of course get different images. There are so I may get just the one layer, though it is assigned red color, doesn't matter. I can change and my multispectral, I will have all layers just in one, and this is component 1, which is having the maximum variability. If I go for component 3, then I go like this, and it will have minimum variability as compared to the component 1. So likewise, you get not only the eigenvectors, eigenmetrics, but also you get 3 principal components. You can always make color composites also, like I will be doing here, and you get such results which are of course the interpretation part of composite, principal component composite is going to be different, but it will provide lot of variations in the pixel values, and one can even go for classification of such a composites, or can use for other interpretations or discriminations of different objects. So, likewise principal component analysis can be done. If image is larger, it may take a lot of time, but if this image was not of very big size, so it took only about a minute, and we get every information very quickly. Now I will go for another technique which we have discussed also. So again I will go raster, spectral, and then decorrelation stretch. So in decorrelation stretch I will, so again the image here, that the same Moscow spot image which I am taking, and where I will put this image, that has to be provided. So I am putting in temp, and just okay. So now I have decided my output, and if you want you can also create output in floating point or whatever, but for time being I am choosing as the default value, and I am asking that it should be stretched also, so that I get a full thing on here. Coordinate system, from where these will come, so let it continue as from whatever they are there, because it is already georeference, so I need not to make any changes here, and then I go for decorrelation stretch. Again it will take some time, it is initializing, and then it will create again a lot of variability, because recall in principal component analysis, when you see in principal component analysis what is done, basically two steps is there. The origin is shifted to the cluster where you are having, then it is aligned, the axes are aligned as per the maximum variability present within one cluster, and that becomes your principal component 1, and perpendicular to that alignment, that axis PC1, there will be another component which is PC2, principal component 2, and perpendicular to these two components there will be another, that is principal component 3 likewise. What we are doing in decorrelation stretch, we are further stretching these principal components and trying that the images, the pixel values should occupy the maximum space available within that three-dimensional space or in a full dynamic range. So likewise we go for more variability present in the images within this this image. So we will now add that image, and this is decorrelation stretched image. As you can see here, I will switch off these one and take this one here, and of course I change this colors, and this is what you are getting here. You can choose different schemes here. Okay, and yes, now just compare this was our original image, and this is decorrelation stretched image. So much discrimination among objects can be made as compared to simple your false color composite. No matter that image, whatever you will enhance will not reach to this stage as you can do it through decorrelation stretch. So decorrelation stretch will create a lot of colors, lot of variability, because these principal component axes are being stretched, and more they are occupying the maximum space which is available for each band or for each component between 0 to 255. This is of course a 24-bit scenario, That means for each band we are having 8 bits or 1 byte for per pixel. So in total three components are there, or 3 bands are there, and therefore you are having 24. But the output, as you can see, that I will again just demonstrate you. And this is your original image. Hardly you see the discrimination, and once you bring this decorrelation stretch, which can be done very quickly, and you get beautiful results. These images then go for classification or simple image interpretation, and in that way the reliability of your interpretation and classification can increase very significantly. And now we go for another demonstration, and that is on this using this public domain software, that is DIBS, because here we can develop better understanding of the things, and then for real processing you can go for commercial softwares. So today in this particular demonstration of using this digital image processing simulator, first I am going to show you the density slicing, which we have already discussed when we discussed the unsupervised classification and density slicing as a one separate lecture. Now, as you know that the main purpose of classification or as density slicing, that there might be lot of variability or pixels having large range or in a continuous image. We want to discretize and create just few classes, and likewise we can do it. And this here in this demo, through this software, we can see either we can see data view as being displayed, or we can see image view. So let's keep data view, because we want to understand how this is going on, and then we will try to add different classes here. So if I quickly scan, and then what I find that in this image the values are, the lowest value here is 10 and the highest value is I think 68. So we will slice down this image into few slices. So what the first slice which we are going to choose is between 10 to this, between 10 to we will have 30 here, and then add values here. Then we go for another slice which is say 31 to having 20 range here, so 50, and then we will go for another slice, and that is 51 to we say 70, and likewise I think we have completed all three. And then when we select this one, then we say okay, slice down this image. Now you see that this image, now we can see the image view and also a sliced view. We have just for simplicity we have created only 3 slices. One can create more slices or more classes if prior information is there. As you can see that the entire image, which has lot of pixel values range starting from 10 to 68, have been sliced down only into 3 classes. So this is how, and this is density slicing is performed on real images. This is a simulator just for demonstration, but it clearly brings out the concept of density slicing here, which you can see. Now the next thing which we are going to see is the classifier, and here what we will do, we will create these training sets or signatures by choosing different. So when I put the cursor on this image or these values I know, so I say that this is going to be my one training set, and then I say and if any value which is more close to this, then I can also include in my training set, like this one of course. If I want to include 9, then 10 is also there. So, I will just at 2 locations, as I was mentioning when we were discussing in the theory discussion about supervised classification, I said within every image it is always better to choose at least 2 signatures or 2 training sets. So, one training set I am choosing, and then I will say put a value here and say that this is a bare ground. All right, and then so now I get our minimum maximum, which I know because only 3 pixels were there, mean and standard deviation. So, statistics also available. Then I choose another set, another training set by clicking here, create new training set, and I say that this black area I want to be as a water body. So, one training set here, and these values are also quite close, but so I choose this as a training set, and then say save signatures here, and then say water body. Again I get the statistics of my training sets and training set water body. Now again I go and create one more class here, or one more training sets using these gray values, which are ranging between 66, 68 and likewise, and one more training set using not this one, maybe okay, maybe this one and this one. So, 2 training sets for this particular class I have chosen, and I, as per my prior information, I am saying that this might be agricultural land. And then I get this one. Now, last one more training set I will choose using these the values here, the light gray values here, which are having value say 91, 80, 93, 89, one training set I have chosen. Another might be in this one 89, and this one is going very far. So, maybe 70 and these 2, and then say okay. So, this might be my say forest. Now, 4 training sets have been chosen. Now, I say that okay, stop collecting and classify. 2 methods are supported here in this demonstration software. One is the MDM, that stands for minimum distance to mean, which we have already discussed in previous discussion on this supervised classification. And second one is parallelepiped. So, in theory class we have discussed 2 types of standard parallelepiped or precise parallelepiped. Here only one option is available. So, I go for minimum distance to mean, and when I go for classification, this is how I get my classification results. All the values which I have assigned are showing different classes. Likewise, so I choose here, and I know that how these calculations are being done, that one can also check for individual classes and see that what kind of statistics is going on. I think something went wrong. No, it is fine. So, now I get I can keep checking my classification results very easily by using these methods. Two methods are available. I can go for another method, again classify and say okay, number of standard deviation, I say just keep 1, and this is how as discussed in the theory class, that two same training set, same image, input image, but two different algorithms in supervised classification, two different results. So, one has to be very careful. Here many pixels went unclassified because I through this demonstration I did not exhaustively collected all training sets. I should have gone for 7, 8 at least training sets, then probably the entire image would have classified in different classes. But nonetheless, in real softwares you can add few more training sets and then again go back and make corrections and then go for classification till you satisfy with either matching with other results or doing the accuracy assessment part. So, those things can be done quite easily. So, we complete this demonstration on classification and density slicing. Now, the last one which is very important in case of classification is about accuracy assessment. So, this accuracy assessment is first as a top one, the top image which you are seeing is basically the classified image which has got 5 classes: water, urban, shrub, forest and barren land. And these classes are there. Now, we go for accuracy assessment, how accurately these classes have been classified on the same image which we have been using. Now, do you want that how many percentage of references should be taken, whether 50% from this total ground reference or prior information which we are having, or 10%. So, if I choose say I want just 10% selection, because the larger the I will go, though I may get different results, but it may take more time anyway. So, I am going for 10% and then choose OK. Then identify simple pixels. So, now there are 77 random pixels on classified image have been identified with reference corresponding to the ground image which you are seeing here, and then finally create error matrix. So, here we get the error matrix which requires little interpretation here, and that is a 2-dimensional table basically. So, here again you are seeing water, urban, forest, all those classes are there, 5 classes as were here, and then again those 5 classes are there, and what you are seeing the total of column or row or diagonal axis is all 5, and total accuracy it is saying that 71.43 is here. So, this kind of quick assessment can also be done in professional or commercial softwares as well. Now, instead of this error matrix, I can also go for a kappa coefficient and can go for calculations again. So, I get only this much of that I will now keep moving through this, and I get the values against this row which is a total column, and then now a row. So, for each cell of this 2-dimensional table, the calculation is being done as you can see, and this is what now results will come. So, I say OK, calculation is complete. So, standard deviation, the matrix summary which is saying that all this it is the diagonal sum is 16 which we are getting, and the grand total of all these kappa coefficient calculation is 49. And again this is likewise how this calculation is done is that the observed minus expected. Expected is coming from these 10% of selections which we have chosen at very early stages. If we go for 50%, I expect that our accuracy will improve further. Because there are more chances of getting more errors if number of random points or random pixels are selected to compare with the classified image. So this is this ground reference image, or maybe after ground truthing, or maybe through some other map. So here some other map has been chosen, and this K kappa coefficient comes around 0.576, which may not be very good, but in this demonstration we have done it. Let's try again the same thing with the 50% and see what happens with this one. And 50% we are going instead of 10% sampling, and then identify pixels. So all those now 32 random points, that means that this one is having total 64 pixels in this sample image. So 30 to 50% of points have been selected, roughly half randomly they have been created. Now we go for this matrix, but what I was saying, it is not exactly like this. The accuracy has reduced. There we were getting this total percentage of accuracy was somewhere about 71. Now we are getting 62.5. So it is not always necessary that you get high accurate results. And of course the same way you go for kappa calculation, and likewise keep clipping for all cells, and then you get this kind of values are there. This is point. So the value is the accuracy part has definitely gone down. Well, this is in that case, in that example, sometimes you may get better results as well. So whenever the classification is performed, either supervised classification or unsupervised classification, accuracy assessment must be done, and in your results, in your report, a statement should also be there that how accurately the classification is. 0.625 is not a very good classification which has been achieved, but nonetheless, and this is how one has to report, so that the real pictures comes out after the classification. When any image which is having lot of heterogeneity in the pixel values, your accuracy is going to be reduced or very less. However, if an image which is very homogeneous, I will give you example. Suppose you are working in a desert area or in a dense forest area or in a snow covered area. There most of the pixels might be having very near values, same values, close values, and your classification will achieve very high accuracy. But if you are working in an area where a lot of heterogeneities are there, and say maybe in agricultural land, small agricultural plots are having different kind of crops, and their spectral characteristics are going to be completely different, and therefore when you assess the accuracy part, you may not achieve a very good accuracy. So homogeneous images which are having homogeneous characteristics or pixel values are close by, then you may achieve a very good accuracy. In a heterogeneous images, you may not achieve very good accuracy. So this brings to the end of this discussion about this demonstration. So first, what we through this commercial software, I did the demonstration about this convolution filtering, how to edit, how to design your own, and then principal component analysis, and how to see the assess the matrix and individual components. You can see a combined composite also you can have, and then decorrelation stretch is in comparison with the original image. and also finally through this DIPS software we have seen the demonstration of density slicing. Similar way you can do it on commercial softwares. Secondly is a classifier, and third one about accuracy assessment. Full time, all the time I am not using commercial softwares, because purpose here is not to promote any software one, and I would prefer to use DIPS wherever it is possible, because it is first of all it is not commercial software, it has been developed in academic institute, and it is better to first understand what goes behind in each processing in commercial software, and that can be only understood through such softwares like DIPS, which I have been using. So, this brings to the end of this demonstration. Thank you very much.